Today we will continue on this kind of workshop sessions where we will try to make you familiarize with Python and all this kind of libraries that we are using for AI. But before that, I will spend some time to introduce for people that they're not very familiar with some notions of deep learning and medical imaging, which is actually our main research topics. And please ask me questions, and let's make this a little bit less boring for you and for me. So please interact with me during the session. Before we start, we met yesterday, but this is actually my main milestones with respect to my academic career. Currently, I am an assistant professor at Central-Supélec together with Stergios, and we are working on machine learning topics applied on computer vision and medical imaging and remote sensing applications. And as Olga also mentioned yesterday, we are from University Paris-Saclay, which is actually a huge university that contains different kinds of disciplines like pharmaceutical universities, medical universities, and as well engineers. So Central-Supélec is the call of this university, and it is an engineering school. And our lab is actually called MIX, and it focuses on applied mathematics and computer science. So it has three different disciplines. One that works on quantitative finance, the second one that does more computer science, and the third one, which me and Stergios we are belonging to, which works on mathematical modeling for biological systems. And in this team, which is actually the biomathematics team, we are working on computational biology, on medical image analysis, on applied mathematics, and in general, everything that has to do with life science. Also, except University Paris-Saclay, we are also affiliated with Archimedes, the new AI center that started here in Greece. And the idea is to work on the same topics and introduce the same topics in the Archimedes structure. So some motivation about what we have seen and what we will be discussing, and I guess you will be discussing as well for the rest of the school. Artificial intelligence has a huge hype the last 10, 12, 15 years, with a lot of kind of interest that comes from very high impact journals and studies that actually they highlight that this kind of algorithms, they can impact variety of disciplines. And actually one of these is actually healthcare. And on 2017, we had one famous phrase from Hinton, which is is considered one of the fathers of AI, that said that medical schools should stop training radiologists now because actually AI will replace them. And of course, this is just one saying. The same thing we can find it for other disciplines, like for example, the lawyers, artists, and so on. We have currently a lot of advances that people are really excited about, and they think that we can actually do everything with AI, something that I would say that in the current state is not true. So, of course, this kind of statement became quite popular, and doctors didn't really like it. But at the end, and what we know now is that we are actually 4 or 5 years after that, and AI still is not applied in the clinical centers. We have a lot of obstacles to overcome still. So definitely we have a lot of kind of work in order to use and integrate these algorithms into clinical practice as well as on other everyday things of our lives. Now I will start introducing a bit about deep learning, which is one of the kind of algorithms that belong to the family of algorithms that Stergios discussed yesterday. So we have all this kind of machine learning or artificial intelligence a family of algorithms where we have cognition-based systems, which are systems that they don't really rely on data. They are systems that we as humans try to control. And then we have all this kind of data-driven and machine learning algorithms like support vector machines, logistic regression we saw yesterday, random forest, and so on, that they are relying on the data. And deep learning is just one part of this kind of family of algorithms that currently that has only very, very small kind of representation on the entire AI ecosystem. And indeed, however, it is very popular and a lot of people, currently it gives quite impressive results for a variety of domains. And what actually we're doing for quite some time with machine learning is that we had all these different kind of applications, like for example, computer vision, medical image analysis, or even speech or analysis of text. And what the community was doing was that we to find different kinds of features, different kinds of representations, like for example, the statistical features that we were trying to extract yesterday from this medical data. And depending on the domain, depending on the applications, we were trying to optimize these features in order to make them more appropriate for the particular kind of inputs and data. And then we were using different kinds of machine learning algorithms, which are algorithms similar to what we saw yesterday, in order to solve a problem, like for example, a classification, what is the particular image, what is the class for the particular image, what is this signal of speech says, or what is the NLP, what is the interpretation of this kind of sentence. So for a lot of years, and actually for 20, 30 years of research, what we were doing is that we were really trying to optimize this pipeline by either finding the most appropriate features to represent our inputs and our data depending on the domain, and also combine them with the most appropriate classifier. And here, actually, for a lot of years, people were really trying to find and modify the classifier such that they will be more appropriate for the particular kind of applications. However, when deep learning arrived, things got very simplified. We had very simple mathematical operators that we could apply in a hierarchical manner, one after the other. And actually, these mathematical operators, they work any kind of input. We don't really need to optimize so much or try to find more appropriate or things to represent the data that we have. And moreover, the good thing about now deep learning is that we don't have to do this kind of feature representation. We don't really need to have this optimization of the features that we will actually extract from the inputs, since the algorithm will do it automatically and will create the features that actually they are more appropriate for the particular kind of task. So in this kind of algorithms, we have two different kinds of advantages. The first one is that we don't to really design and spend time to find the most appropriate features. And the second one is that exactly the same operators or very similar operators, they can work very, very well for different kinds of inputs. So we really gain a lot of time, and actually this is quite impressive. And this is actually what was happening. So in case of the classical machine learning, what actually we did yesterday, we had our input. We had to design our features, all these kind of statistics that we extracted yesterday. And from this, we use a classifier to do the particular task. Now with the deep learning and what we will do today, we have our inputs and all this kind of representation from the feature extraction to the classifier and the output. It is happening inside the algorithm. It is optimized. Both the features and the classifiers, they are optimized. They are trained exactly on the same time. And what are these kind of features look like? This is kind of a big question, and it had a lot of kind of interest in the beginning when actually convolutional neural network came into the game. So actually, again, we have this kind of features which follow a hierarchical composition. And from each of these features, we can actually visualize or see what actually the algorithm learns. And what actually we observe is that on the first level of the architectures, of the features that we are using, the algorithm actually learns features that they are more close to the image in the sense of, you can see here, for example, some features that they highlight color or lines or some kind of or edges or in different kind of directions. While when we go deeper into the architectures, we have features that they are more abstract, and actually they are going towards more close to the class that we want to identify. So for example, if we have an image of the car, you can see that on the last level we can see parts of the wheels or different kind of things, or even we can identify features that are closer to the other kind of classes that we learn together with the image of the car. So indeed, this is quite interesting, and this is very and actually using all these kind of handcrafted features that we have developed all these years. I would say that we were more on this kind of settings. We were able to reproduce these kind of features which are focusing more on texture, on lines, colors, and so on. All kind of information, it was very, very difficult to reproduce or to find them with the mathematical operators that we had until that point. And what is actually a definition of deep learning? This is one actually that I like. So deep learning is nothing else than a family of parametric, non-linear and hierarchical representation learning functions, which are actually massively optimized with stochastic gradient descent to encode domain knowledge. And why actually we have this parametric? Because as we saw yesterday in the, for example, logistic regression, we have parameters that we need to optimize. We have some kind of weights that we need to learn during the training process. Non-linear and hierarchical representation. Non-linear because actually we have non-linear operators that they are integrated into the process, and hierarchical representations because we have this kind of hierarchy where actually the output of one kind of module, one kind of operation is actually the input of the rest. So we have this kind of nest here where actually the output of the one operation, which is nothing else than the function that we are using in this level, it is inserted as an input to the next one, and so on until we are actually ending up with all the operations for the particular kind of function. And again, we optimize it. Stergios mentioned it yesterday a little bit, using optimization algorithms. Stochastic gradient descent is one of the most popular ones that it is used on machine learning, and in particular for deep learning, the one that it is actually used with modifications depending on the time and depending on the trends. So now we have much faster and much more efficient optimizers than the classical stochastic gradient descents that we are using. And this is nothing else than the loss function, the objective that we want to optimize, which can be, for example, the class that we want to obtain for the particular input, to minimize it with respect to all the parameters or the weights of the architecture that we have, of the algorithm that we have. And since deep learning is quite popular, we can have different kind of architectures architectures that we can use, and you can actually in the literature variety of architectures that more or less they use similar modules or different ones depending on the task that we want to solve. For example, we have this kind, the first ones, which are actually this kind of simple perceptions where we have only one layer, or we have more deep ones. We have recurrent neural networks, which have this kind of circular units here in order to encode, for example, temporal information. We have the kind of autoencoders that we will see also in the lab. This is the kind of architecture we will be using. And of course, this comes with different kind of structures and different kind of modules. So of course, this is quite, you can find everything you want in the literature. However, for images that we will focus on this kind of work on workshop and for the rest 2 hours, the most popular architecture that is used for the last 10 years is actually the convolutional neural networks, which I will actually focus for the next few slides. But however, even if it is only one family again of algorithms that we use, we can find different kind of architectures. Some of them we can see them here, which are actually compared with respect to their performance and the number of parameters and their size. So you can actually choose everything that you need depending on the application and the thing that you want to do. And as Stergios presented yesterday, deep learning algorithms and networks, they have been used in the beginning, or they have been initially proposed in a supervised setting, meaning that we needed actually to have this kind of annotated set, where for each input we need to have actually a label, and using this kind of label we're able to solve and optimize the parameters of the network. However, later on, and since this could be a kind of limitation in the case, for example, we don't have so many data, medical imaging or the medical field is one of these kind of situations. There are other types of learning that they have been introduced, and they are actually trying to use exactly the same setting, but this time without labels. We were trying actually to optimize them using an unsupervised, using, for example, unsupervised learning, where here, for example, we have an image and try to reconstruct exactly the same image. And during this process, we are able to learn all the parameters of the networks that we have here. Or other kinds of learning, as for example, the reinforcement learning, or other tasks that they are actually belong to the image, and we don't really require any kind of annotation. And in case we have this kind of setting and we are able to train our models with this kind of settings, we are able later on to use their parameters for the supervised for supervised things. And since we will focus, and in the lab as well, we will see we will talk about convolutional neural network. Let me introduce the convolution. So overall, one thing that we discussed also yesterday is that images, they are actually 2D signal or even 3D in case we have medical data. We saw yesterday the MRI scans, and we will see them as well today. And since we have this kind of 2D inputs, we have this kind of matrices and arrays, we have also information that doesn't contain only the intensity of the pixels, as we discussed, but it contains as well a kind of notion of the neighborhood on the actually pixels that belong next to each other. And these actually pixels are quite correlated in case they are close to each other. So the convolutional operation, it has been actually invented some years ago in classical computer vision, and it is nothing else than an operation that takes the input, and it is actually calculate the weighted average of each of the positions of the input with the kind of kernel or which has actually weights that they have been predefined beforehand. And this kind of kernels, there were a lot of research how we can design them, how we can prove which ones they are better and which ones are for which purpose more appropriate. And for this kind of for here in these slides, I use this kind of kernel which indicates or tries to identify lines that they are on the horizontal direction. If I rotate it, I will be able maybe to, not maybe, I will be able to identify the lines or the edges that they are on the vertical. So this kind of, the convolution operation is something that we know. However, in this kind of classical application, we need to have the parameters predefined, and we need somehow to know what actually they will give as an output. So this is something that this is what was happening before. With the introduction of when deep learning started, the main idea was, what if we have exactly the same operation, since it can be integrated on the entire deep learning pipeline, but instead of having these predefined parameters, these will be the parameters that the network will try to learn automatically from the data. And if we do that, maybe we will be able to identify all these kind of features that I showed, that they are more appropriate for the particular kind of application. They are for a particular kind of reason. So again, here, the main idea is that we apply this kind of operation, the convolutional operation, but instead of applying it with predefined parameters, we learn these parameters and we don't apply one or two filters, but we apply a lot on different kinds of representations in a hierarchical way, as we saw before. And how we do this kind of hierarchical way? One main modules that we use is actually the pooling module, which tries actually to reduce the spatial resolution of the image or the features that we are using. So usually after one or two convolutions that they are applied one after the other, we have a pooling module which reduces spatially the dimension of the feature. And why we do that? We do that because, first of all, we reduce the size so we can make all the calculations faster, we can feed data into the memory, we can calculate more filters, we have a lot of advantages. And the second one is that we change the view of the convolution is actually applied, and with that way we change something that is called the reception field, and we were able to learn more complicated and more abstract features. And there are different kinds of ways to do a pooling module. There are two that they are most of the time used, or actually max pooling is one of the most popular, where here we have our image, and for each of these kind of sub-regions we select the maximum value and we put it as an output to the after pooling matrix that we have, or the average pooling, where here we're calculating an average of all these kind of regions. And okay, so any question until this point? Everything was clear? Yes. Actually, this is okay. Very good question, because in general, what is true is that when we are talking about all this kind of architectural kind of choices, there is no kind of proof or thing that you know that one will be working better than the other. So most of the times you have to empirically try to find which one works better for your application. But most of the time I would say that max pooling is by default used. Like, for example, we know that ReLU which is one of the nonlinearities. It is the one that usually people choose in order to integrate into their architecture. So this is actually, you can see it as a hyperparameter, something that you need to define when you will develop your architecture. Okay, then we can continue. So how this kind of features looks like? We saw one some kind of example before. Here we have more. We have for the first layers, you can see that we have actually activations that they are more looking to colors, to edges, and so on. When we go to the second layer, we have activations and features that they are more close to the structures of the image, and then as we go deeper into the architecture, convolutional architecture that we have more structures that they are more close to the class that we want to find. And of course, for the fourth and the fifth, something, yes, we have again features that they are very, very close to the image and the class. And one of the things that we discussed is that how we can actually find the best or find the best architecture. So, a good answer on that, and that's why you can find in the literature a variety of different kinds of architecture, that it's up to you to. One of the first ones that was very popular for convolutional architecture was the VGG, and there were variations of this kind of architecture, which has been developed from Oxford and the VGG group. And here again, you can see that it is nothing else architecture than apply different kinds of convolutions one after the other, and then we have again the max pooling operation here, and we go deeper and deeper into the architecture until we have here some kind of fully connected layers, which will do actually the final classification that we want for the particular input. And one more architecture that was quite popular, and it has been developed by Google back then, was the Inception, where here you can see that this architecture was much deeper than the previous one. It has much more levels. And the main kind of idea here was that the researchers, in order to train such a deep architecture, they integrate different classifiers on different kind of levels of the architecture in order to be able to update the parameters of the network back to the initial layers. However, one of the most interesting and let's say used convolutional architectures even now, the ResNet family of architecture, which was actually a breakthrough back then, and it is again even now used as a default convolutional architecture, where we have here nothing else than some kind of the same kind of structure, but instead of having only this hierarchy, we have this kind of residual connections that connect the input with the output of the convolution for the particular layer. And this connection, it can happen, for example, with an operation of an addition. And this is actually seems to work very well and have a lot of advantages on training and so on, to be able to have much deeper architectures. And it is actually quite popular, and it is performing very, very well. And since it is performing so well, there were a lot of kind of other architectures that they are trying to build with on top of ResNet, as for example the ResNext and so on. However, I would say that even today ResNet by default the architecture that everybody starts when it starts with a classification problem. Any kind of question until do you have any question until this part? Yes. Yeah, so very good. So, very good question. So, as we saw yesterday and as we will see today, when you perform your training, you kind some kind of metrics that you actually calculate all the time in order to see and assess how good or bad it performs. These metrics, they can be on the validation set, they are reported on the validation set, and of course on the test set and so on. Now, the best one is the one that it will be better, will be best with respect to this kind of metrics that you chose. But for example, in case you have more complicated questions that they can be, for example, more clinical oriented, maybe you have let's say a model that doesn't perform the state of the art for a problem, like for example to segment very well the pathology, but maybe this model can give you features that they are very interesting or very important for the clinical endpoint that you want to solve. So again, this is up to you to define what is more important for you, as well as, for example, when we are talking with clinicians, sometimes they want to enforce, for example, not to have a lot of false negatives, not to lose a lot of cases, even if they have more cases that they have been classified in the particular class. So in that case, maybe you can choose a model that has this kind of characteristics in with respect to another one. Correct. Correct. And one thing that it works as well, and it is most of the time, this is one question is how do you know that this is the best that we can get? So most of the times you ask humans or experts to perform the task as well. So you have a kind of evaluation with respect to the human performance, what you can expect. And if your model is close to that, or it's not, yes, it's maybe the superior, or it is lower than this kind of metric, but close to it, maybe you are good enough to use it in the application that you want to. Yes. Correct. So for this, usually, okay, so most of the times you do a kind of pattern recognition task in order again to perform something like a classification task at the end. For example, you want to recognize a hand of a human body because you want to recognize that this object it's actually a human. So again, you have at the end an endpoint, but also you need to define metrics that they are actually good for the task that you want to detect. So, for example, if for your application you want to be very accurate on detecting hands, you need to have some metrics and some evaluation and some ground truth with respect to these objects that you want to look for. Okay, good. Anything else? Okay, in this case, we will continue a bit on the second part, which is actually the part of the medical imaging. So we saw yesterday some of them, and actually we analyzed images that they are coming from MRIs, and this is what we will do also today. But we can have different kind of different kind of medical images that they are used in clinical practice, as for example the X-rays, the CTs or PET, and of ultrasound, and of course we have modalities, as for example that they are working on the microscopic level, so we take them from microscope, like the digital pathology ones or other kind of microscopic images. In general, medical imaging is the most way to see inside the human body without actually performing any surgery. So it is very widely used in the clinical practice for diagnosis. And it is non-invasive. It is completely non-invasive. You don't have to really make anything into the human body. And of course, depending on the modalities that you will use, sometimes you can even find things that even if you do an invasive surgery, you will not be able to see with a naked eye. As for example, you can observe metabolic or functional or molecular activities, things that they are not really visible with the naked eye. And of course, since this is something that we are really using in clinical practice, we have different kind of things that we want to identify, as for example, to do the image processing of this kind of modalities, for example, to improve the quality of images. We can do some kind of machine learning in order to identify different kind of tissue, different kind of classes, and of course, at the end, to have a kind of semantic description and understanding of what is happening to the particular sample. And medical imaging, it is used, first of all, we said, on the clinical practice and the medical care. We use it in order to detect lesions and anomalies, to do screening, quantification, to follow up pathologies. But also it is used in the research and a lot, for example, to automatize the clinical process. This is actually what all of us we are working for prognosis, or trying to go one step forward by finding maybe the people that will respond to a particular kind of treatment, something that currently it's not very easy to do. Even for the doctors, and also try to understand the alternation between specific type of diseases, try to use it and combine it with other kind of data, like for example genetics, in order to find again and try to stratify patients with respect to these characteristics. And some characteristics of the medical imaging, depending how on the modality, we have either to process a 2D signal where we have only X and Y, only a 2D input, or we have 3D signals where we have again the X-axis that will contain also the transverse plane over the human body. And again, the major modalities that we are using, and actually we can find a lot of kind of literature. It is actually the X-rays, the CT scans, the nuclear medicine or PET, ultrasound, MRIs, mammography, histology, and so on. So there are a lot of kind of modalities that we can use. And these kind of modalities, they are actually working in different ranges of the spectrum. So here is the spectrum that our eyes is able to interpret and see. And you can see, for example, that the MRI works on this kind of spectrum, where here we have, for example, radio waves, or the CT and the radiology, it works here, and the nuclear or the PET images, they are working here. So depending on the spectrum, we can have different kind of signals that they can give us different information for the human body. And since this kind of modalities and this kind of machines, they are actually there is a rapid research advances on this kind of technology. The field of medical image analysis is quite active, and we have a lot of research and a lot of movements on this field. We are working on that. Sotiris is working also on this, so we can verify that. We can actually help and do and provide improvements on image quality, on trying to identify clinical requirements, or trying to create algorithms that they can assist again the clinical practice. And again, often we need to deal with multidimensional signals, which are 2D, 3D, 4D, or ND, and they can have actually very dynamic range. So, for example, a high-resolution MRI image of the brain, the images that we are using for the practical, They can even contain 300 slices on 512 by 512 voxel sheets, which you can see that the dimensionality is very big and even bigger than the most of the kind of computer vision data. And also some kind of modalities, as for example, the digital pathology, they can be huge in size. They can actually you can have actually gigabytes of require gigabytes of size. So actually, yes, thank you. So actually, this is something that we need to know when we want to process this kind of data. And how we can actually use deep learning or this kind of data, it is quite challenging. However, it is a topic that is quite active, and actually the last years we can see that deep learning algorithms, they are more and more used for all these different kinds of implementation, detection, classification, on different kinds of modalities, like for example MRI, microscopy. These are the modalities that deep learning first starting to be applied. Now we have algorithms, sound, X-rays, mammography, and so on. And also they use to segment and find different kind of things, like for example pathologies, brain, and there's to abdomen or cardiac applications. So you can see that it has a very, very big impact for a variety of modalities and variety of applications. Moreover, we can have a different kind of applications for how we can optimize the image acquisition. There are people, for example, and there are studies that they are trying to reconstruct CT with a lower kind of with not so very accurate inputs in order to reduce the radiation that the patient receives, to do some kind of image enhancement, semantic segmentation, quantification, and biomarkers. This is something that we are really also very interested to work on, and this is actually where radiomics belongs to, what we saw yesterday. We have the disease detection, diagnosis, and the disease prediction. And what are actually the challenges that we need to solve on the medical field? So, as may know already, we need to work on a limited amount of data. We have data sets that they are very, very small. So all this kind of data that they are available for computer vision, for natural language processing, and so on, they are not really available for us. So using this kind of data-hungry algorithms is not very easy. Moreover, if we even have this data, the amount of annotations on the anomalies that we want to find, most of the time is very small, which again creates some issues with the biases and so on. And then we have variations in the annotations that they are giving from the doctors. Different experts can actually annotate differently even structures on the image. So here we have a question how we can deal with this, which actually is the best annotation that we can use. Variation that they are actually due to the difference of the sensors, difference of the parameters. There is a lot of research on how we can generalize these algorithms on data coming from different hospitals, from different kinds of people, like with different sex or with different kinds of demographic characteristics. And all this, of course, they are related to the biases that we can have on the data sets and the AI algorithms that they are built on. And moreover, we don't have any explanatory power. We know that these kind of algorithms, they can work well. However, they cannot give us the interpretability that we need in order actually to justify the decision that this algorithm takes. And in order to solve this, most of the times, and now the community actually tries to build public data sets, like for example, the Luna, the Brats. The BRATS is actually the data that we were looking during these 2 days in our practical session, the TCGA and so on. There are a lot of challenges, the public data sets that we can use to build our algorithms. We can actually try to work on the multimodality, integrate different modalities, use algorithms that we are not so much in need of a lot of annotations, like using techniques that they are coming from transfer learning, few-shot learning, zero-shot learning, and so on. We try to create data sets that they are quite variant with respect to the annotations. We ask different experts to have different kinds of annotations. And of course, we are trying to work a bit also on the explanation of this kind of algorithms, how we can actually be sure for the particular kind of decision that this algorithm take, or how we can, for example, identify samples that they are completely out of the distribution of the algorithm that we have trained. So all these are very, very important questions. And to solve this, these are the main, some of the topics that the community is focusing on. Try to build algorithms which are algorithms that they are trained with limited amount of data, that they have some kind of domain adaptation, they can generalize on variety of data. We can have try to specify the metrics that we will do the evaluation and see how we can decide which algorithm is very important. This is a very important topic for our field. How we can actually use all the 3D nature of the data. This is something that we are more and more better on this, since also the hardware is getting better. Try to create algorithms that they will be able to segment different kinds of organs and objects very accurately, and they will be able to be integrated on the clinical practice. And these are actually some kind of algorithms already integrated on the clinical practice. We have this kind of AI tools that they can give you segmentations of organs in a few seconds, making the life of the doctors much easier. Which we want to know how we can fuse data, how we can integrate different information coming from different kind of source of data, how we can use self-supervision in order not to have all this need for the annotations that we don't have access to, and of course all these kind of different problems like resistance, segmentation, classification. And actually for the rest of the day, what we will see as well on the second part of the workshop today, we will focus on the segmentation algorithm and how we can create deep learning algorithms that they will be able to segment very accurately regions of tumor from MRI images. So this is what we will work on. And since we will work on that, let me use some metrics that are usually used in order to evaluate the performance of the algorithm. One of the very, very popular metrics that we use for segmentation algorithm is actually the dice coefficient, which doesn't do anything else than try to calculate the proportion of the true positive samples divided by the sum of the true positives, false positives, false negative. So actually this is nothing else than an F1 score for the people that they are a little bit familiar with that. And of course, the one metric that usually we are looking for when it comes to segmentation algorithms is the Hausdorff distance, that try to measure what is the maximum distance of the between the contour that we have from the segmentation we get and the segmentation that we have as an annotation. And one more thing is what kind of objective functions we can use in order to train this kind of algorithms. And here, most of the times, we are trying to use losses that we are actually able to evaluate our performance as well. Usually this helps. So that the dice loss is one of the popular one. I think this is one we will use as well in the lab, that tries again to penalize this kind of metric when we are training the network. We have also the generalized dice laws, which are here we have different kinds of categories. And then we have more losses that they are more specified, they are used in case we don't have so much data and we need to somehow give more importance on the really difficult to evaluate, as for example the focal loss. And actually, the most popular convolutional architecture that it is used for segmentation, and this we will implement as well in the few minutes. It is called actually UNet. This is a paper that have been published on 2015. And after that, people are really using it, or everybody is using it for segmentation purposes. Again, here, this UNet architecture is a fully convolutional architecture, which has characteristics that we saw before. It has this kind of convolutions that they are applied one after the other, and then we have some pooling operators that reduce the size of these features spatially. And we have again some kind of convolutions that they go deeper and deeper into the architectures until the levels that it's up to us to define. And of course, we have again this kind of skip connections that connect the one side with the other and transfer spatial information that we lose when we do this kind of pooling operation. So UNet was a breakthrough, and it has been, in the first paper, it has been actually used to segment cells, and they proposed as well to have a kind of loss in order to penalize wrong segmentations in the borders of the cells. But after that, it became very popular. And actually, what people are doing is actually to build upon this architecture, and you can find a lot of papers that are trying to build UNet on different kinds of tasks. One of the algorithm that was a bit interesting is this attention UNet, which integrates this kind of attention model, which is, again, you can see here this UNet kind of shape, which is the same one as the one that we saw before. But we have this kind of modules here, which contain some kind of activations in order to create attention maps that will show and they will focus in the most important regions for the particular kind of segmentation. And of course, this kind of UNet, the UNet, it has been extended on the 3D, in the 3D setting, since again, we have 3D images when it comes to medical imaging. So we have again this kind of, we had on 2016 this 3D UNet, a paper that just, instead of having 2D convolutions, we apply 3D convolution, which is nothing else than specify a command into the library. And again, you can see the convolutions, the downsampling, and these kind of skip connections and connect one part of the encoder with the other part of the decoder. But of course, when it comes to 3D UNet, one problem that we have is that we cannot really fit big images into the memory, having also in the memory the architecture that we want to train. So most of the times what we do is this kind of tiling process where we are taking some parts of the data, and these subparts is nothing else than some 3D matrices that contains all this kind of 3D application, and these patches, they are passing through the architecture or our UNet or any kind of architecture, and they will have a kind of segmentation, which after that we can reconstruct again the volume, and we can have the segmentation for the region that we are interested in. So this is something that it is quite popular. And actually, a paper that came in 2021 in Nature Methods, it's a paper that is called Not New UNet. And that paper was actually trying to try to optimize all this kind of things that we want to apply or we want to optimize when we are trying to train a unit architecture. So again, until this point, all the people and all the research community that was working on segmentation was trying to ameliorate the performance of units, just modifying more small part, applying very small modifications. So here, these people, they said that instead of trying to do all this kind of research on optimizing the different kind of parts, we will just try to optimize the parameters that we have, and we will train the network. So actually, this kind of method and this research lab test and apply and actually compete on variety of challenges that they were active back then, and they won the first place on a lot of them. So they prove that they are quite robust. And overall, what the main observations that they had in order to do this kind of to do this kind of research is that they wanted to minimize the time we are actually using in order to optimize the architecture. The success that depends actually on the researcher and the person that will do indeed the experiments. And actually, this is something that we really need to repeat in all the different kinds of data sets, on all the different kinds of challenges that we need to apply. So they actually divide all the parameters that we want to optimize on 3 groups: the fixed parameters, the rule-based parameters, and the empirical parameters. And what they proposed is just this kind of framework, which is you can download the framework of the NN unit, and it is very easy for you to use it. And during this kind of framework, all these kind of parameters, they are automatically optimized for you. So you don't really need to decide about the architecture or the parameters that you will use. You will just give to the framework your database, and then with respect to this database, you will be able to find the best structure that is based on unit and give you the best performance. And indeed, they did a lot of experiments and they participated in a lot of things. For example, also BRATS, the data that we are using, and using very small modification and this kind of automatic optimization of the parameters, they were able to actually beat and be in the first place. So and now I know it's time for the break, but before we go for the break, I would like maybe to conclude this presentation in order to have some time to set up for the lab. So deep learning is very popular. However, we have a lot of things that we need to optimize and all the parameters that we need to do, as for example, when it comes to the architecture, what is the depth, the width, the scales, what kind of modules we will use, what kind of loss function we will use with respect to the problem and the data we have, the optimization strategy that we didn't really talk a lot during this lecture, how we will normalize, we will pre-process the data. And overall, we have a lot of things that we need to optimize. And of course, even if we select out this, it's not like we press a button and everything will work out of the box. We really need to keep track of on what is happening on the training and validation curve, what a kind of check how the network performs on very few parameters, or how good is on the test and validation set, and how we can actually pre-process the data with the best way for the application. And actually, in at least on the medical challenges, the winning teams are actually the teams that they are spending more time on processing and understanding the data than actually create a novel method with respect to all kinds of other characteristics. So it is very important.